Everyone. Today I'd like to talk about learning from knowledge bases, learning from and for knowledge bases. This is kind of a shift from a lot of the stuff that we've done so far. And I'm going to be talking about like a different information source, some relatively different algorithms compared to the stuff that we talked about up until this point. So, it might be interesting, it might be different. So I'll get started with that. So I'm going to be talking about knowledge bases, and knowledge bases are basically structured databases of knowledge, and they can contain a lot of things, but most commonly when people are talking about them, they are talking about relational knowledge bases that include things like entities, which are nodes in a graph, and relations, which are edges between nodes. And I'll talk about some examples of this in a little bit to make that a little bit more concrete. And then some of the questions that we ask about these are, how can we learn to create and expand knowledge bases with neural network-based methods? And then the second question is, how can we learn from the information in knowledge bases to improve like neural network models or use them in effective ways? And how can we use structured knowledge to answer questions? So the first thing I'd like to talk about a little bit is types of knowledge bases. And they come in several different varieties. The first one I'd like to talk about is a very classical one called WordNet. Has anyone actually ever used WordNet before? I see at least one person raising their hand, so it's not entirely, hasn't entirely disappeared. Has anyone heard of WordNet before? Okay, more people. So basically, this used to be a really big thing in natural language processing. It's not so much anymore. But I want to explain about it because I want to explain why this is maybe like less necessary to use, but actual knowledge bases are still more necessary to use. And so WordNet is a large database of words. And specifically what it does is each word or something they call a synset is a node. And then there are relationships between nodes. And the nodes can correspond to nouns or verbs or adjectives. And nouns have different types of relations between them. So they have things like an is-a relation. So like a hatchback is a type of car. There are part of relations where a wheel is a part of a car. And they also make distinctions between types and instances. So like Joe Biden is an instance of a president, and president is the type. So verb relations are ordered by specificity. So like communicate is more broad than talk. So talk is, generally a subclass of communicate, and then whisper is generally a subclass of talk. So it's ordered in this way. And then adjective relations are mostly antonyms. So like wet versus dry and other things like this. When I said synsets, actually each node is not a word, despite the name WordNet. It's a set of words that all have the same meaning. So you might have artifact and thing would both correspond to this node because they both mean basically the same thing. So it's like sets of synonyms. And this is also important when we talk about other types of knowledge bases as well. And so what was this used for? This was used for example, trying to figure out trying to find all the cars that were mentioned in like in a large set of text. So you would go through, you would identify all synsets, or you would identify all words that corresponded to these synsets, and then you would take a step up and find motor car, and you would know that like all of those were mentions of cars. So like, why don't we use WordNet very much anymore? Any ideas? What would you do instead if I told you find all the cars in a big piece of text? Yeah.
Do something with the embedding.
Just do something with embeddings, yeah. So you might get something and find all things that were close in embedding space to a car. What's another thing you might do? Like what I would do is I would download Mistral and say, does this sentence talk about a car? And it would say yes or no. And I would, or I would say, find all the cars in this that are mentioned in the sentence, and it would get them. Sure, that's like expensive, but it's really easy. So, there are other options that might be less expensive, but that could solve a lot of the things. So WordNet, started out with more and more, it started out being very popular in natural language processing, but now it's less so because we can get a lot of it from embeddings. We can get a lot of it from language models itself. Another thing that started maybe before WordNet or even around the same time as WordNet was this database called Psych. And it was a manually curated database attempting to encode all common sense knowledge. The project itself lasted for about 30 to 40 years. It might even still exist. And so they had this huge like hierarchy of all the different types of knowledge you could have. It encoded knowledge about like events and like which events happened before other events and all these other stuff like this. But the problem with this is this was just too ambitious, basically. It was not possible to encode all of this manually by hand. So people like it got part of the way there, but that part of the way there was not enough for it to be really useful in practical systems. So it isn't, this sort of method is not used as frequently now. A follow-up one, which is its successor is now the most widely used knowledge base, is something called DBpedia. And the basic idea behind DBpedia is that while Psych is too difficult because they had people on the Psych project who would go in and curate rules for machines, Wikipedia, basically, they have a very, very large number of humans curating this structured data about entities in the world for humans. They're creating it for humans because then you can put it on a Wikipedia page and you can look and see it says Carnegie Mellon University. It has the former names of Carnegie Mellon. It has the motto of Carnegie Mellon, the type of entity, who it was established by and when, and other stuff like that. And because people were no longer creating it for machines, they're creating it for humans, people are like motivated to do this. So like lots of people will do it for free, so you can actually get a reasonably sized amount of data from this and actually cover, like most of the entities in the world. Or not most of the entities in the world, but most of the notable entities in parts of the world that have high participation in Wikipedia. So now the thing that a lot of people use is something called Wikidata. This name is a little bit of a misnomer because it's not actually that closely connected to Wikipedia. They extract data from Wikipedia, but they also extract it from lots of other sources. And this is a curated database of entities. It's linked, it's extremely large scale, and it's multilingual. And this is an example of a thing from Richard Feynman, where people can go in and they can actually like add information and stuff like that. And it gives information about education and all kinds of other stuff. So for fun, I can go to the Wikidata site. Does anyone have an entity they'd like to know more about? Any ideas? Maybe something that has been in the news recently, or nobody brave enough to come up with an entity? Yeah. Mamba. That's a good one. I'm actually not sure if that one's going to be in here. There's lots of Mambas, but I don't know about that particular Mamba. Let me see. Do you want to know about a different Mamba? Do you want to know about Mamba, the research group? So Mamba is a research group. It's the Modeling and Analysis for Medicine research group. It focuses on mathematical biology, and it's in this National Center for Scientific Research in France. The chairperson is this person and stuff like that. So you can see it has all of these things. So Mamba, this Mamba is a node in the graph. And then the edges are pointing, the edges are labeled with like instance of, and then the next node is research group. So research group is like another node in the graph. And so you can click through this and it has its own ID and other things like this. Also, you'll notice that research group is translated into lots of different languages in the world. So you can use it multilingually and other things like that. Even minor entities like Graham Neubig are included in this, and it has a little bit of like information about me, like my PhD was in Kyoto University in 2012. I am a human. I am male, and first name, last name, university teacher, computer scientist, natural language processing. This is all right, because this is mostly hand curated. It even has the IDs of my advisors. The reason why it has all of this stuff actually is because like 15 years ago, or like 10 years ago, I entered in my my information into the mathematical genealogy project, which is this project about who your advisors were, because I wanted to see like who my mathematical like siblings were and stuff like that. And somehow they managed to pull that out and keep this like 10 years later. So basically they're pulling information from like many different structured data sources that they can use. So they can pull it in there. I don't know where they got that I'm human, but maybe that was inferred from some piece of data somewhere online or something. Cool. Another good thing about this that actually I didn't mention directly in the lecture note or slides is that there's a query language for this. And a query language, this query language is called Sparkle. So there's a SQL for querying relational databases, and Sparkle is for querying these knowledge bases. And let me see if I can, I asked ChatGPT to write me a Sparkle query to find all presidents of Carnegie Mellon University. So let's see if ChatGPT is capable of doing that. Okay, that's a problem. Let me see. Okay, there's an error in there, but like if I could find I don't want to waste time in class like finding a working query, but basically you can put it in a query and it allows you to do a lot of things that are similar to what you can do in SQL. So you can find like all of the edges of nodes that satisfy a particular relation. So you could say, I want for Carnegie Mellon University to find all things that follow the like president of relation. And that would give me all, you know, all presidents of Carnegie Mellon University. You can also like filter by their start date and end date. So find all of the presidents between a certain time and another time or things like that. So this is good if you want to get like high reliability data in a scalable way, because like if I ask ChatGPT, like one of my favorite queries for ChatGPT is like name all of the presidents that were born east of the Mississippi River. And I've never successfully gotten ChatGPT to be able to do this because there's lots of presidents who were born east of the Mississippi River, and it starts counting them. It can't distinguish what position is east of the Mississippi and what position is the west of the Mississippi. But if you write a like a Sparkle query, it's not that hard to do that. So there are there are certain types of questions, especially information aggregation and complex relations and stuff that language models are not very good at. Cool. So that's kind of an intro to knowledge bases, why you might want to think about them. Any questions so far for discussion? Okay, I will move on next. So the next thing I'd like to talk about is learning representations for knowledge bases. So knowledge bases are great, but one problem is they're like inherently incomplete. And even with extremely large scale, it becomes impossible to have them be complete. And the reason why is, for example, in Freebase, which was the predecessor to Wikidata, 71% of humans didn't have a date of birth. And probably every human actually has a date of birth, right? We're pretty much guaranteed for that to be the case. So the issue is, like, for very famous entities, you want lots of detailed information. Like, you can know absolutely everything about Joe Biden or Barack Obama, but, at the same time, for less major entities, you still want them in the knowledge base, but you're not going to be able to get all that information, nor should you, for privacy purposes. And so the idea is, for information that's written on the internet somewhere, can you perform relation extraction, which essentially allows you to extract this information and create your own knowledge bases and stuff like this. And this can also be useful if you want to create it for like a specialized domain or other stuff like that. So there's a bunch of ways that people do this. And one kind of popular way that people have tried to do relation extraction is through leveraging consistency in embedding space. And so this is the most famous example from Word2Vec, what seems like ages ago, in 2013. And in the Word2Vec paper, one of the big, exciting things was essentially they demonstrated that vectors in embedding space had kind of inherent, meaning, and actually the vectors in embedding space could correspond to relations between embeddings. So like we would have man pointing to woman in approximately the same direction that we had uncle pointing to aunt and king pointing to queen. And so then you could do things like you could take kings, subtract out the vector that corresponded to plurality, add the vector that corresponded to, to going from masculine to feminine words, and then like re-add the vector to that were plural, and you'd be able to identify the plural by just knowing these two vectors, the plural of queen by just knowing those two vectors. But it turns out that you can either learn embeddings from you can either learn embeddings from text, or you can use the fact that you have a big knowledge base that was curated by humans, like Wikidata, to improve the embeddings of a neural model itself. And so another pretty large research area that a lot of people have focused on is how do you get good embeddings of a knowledge graph? And this is important if you want to do any sort of like knowledge graph search or other things like this. Like, for example, one of the really nice things about knowledge graphs is they have information about a whole bunch of really sparse entities that aren't mentioned very much on the internet, for example. And so because of that, you can leverage the knowledge graph structure together with text to learn better embeddings overall. And so this particular paper is one example of it. And the way they do this is they express knowledge graph triples as additive transformations. And they minimize the distance of existing triples with a margin-based loss. So the way they do this is they have the head in the tail, and L is the vector corresponding to like the link between the things. It corresponds to a relation. And so you go, you have H and T, and here, like this is L, but here it's written as R because I got this from a different paper. And basically you try to go from H to T according to the relation vector R. And you use a hinge loss where for the hinge loss, you have a hinge parameter, and then you try to upweight the example of a true triple and downweight the example of a false triple. So this could be one that was like randomly sampled to be incorrect, for example. One interesting thing about knowledge graph embeddings is like a lot of famous AI researchers got their start in knowledge graph embeddings. And so Richard Socher is one of them, if you know, he's the CEO of U.com search engine now. And this was a first attempt at predicting relations. They basically created a MLP that tries to predict whether a relation exists. So they have a matrix for the left side of the relation, a matrix for the right side of the relation. And then they feed in the embeddings of each of the entities in the relation. They have a nonlinearity, and then they have another vector that tries to predict the probability of the actual relation being correct. So you would run this through a sigmoid, and then if it was 1, the relation was likely to exist. If it was 0, then the relation was likely to not exist. And then they also propose something called a neural tensor network. And this adds a bilinear feature extractor. And so basically what this is saying is we have the embedding here, we have a matrix, and then we calculate the dot product between the embedding after transformation. It looks a lot like attention, actually, in a way, because we had the bilinear attention, so it's similar to that as well. And then we also have the MLP. So this part corresponds to the MLP, and then we have a bias term. And this is a powerful model, but it's a bit over-parameterized. So actually later, this kind of fell out of favor towards these more simple models that were using kind of just linear projections between the two. So there's a lot of methods like this. These methods are basically assuming that we have either knowledge graph embeddings, and we want to learn relations, or they're assuming that we don't have any information at all about the knowledge graph, and we want to learn the knowledge graph embeddings themselves. It's been used for both of them, but I'd say now it's probably most useful for learning knowledge graph embeddings if you want to do any sort of knowledge graph-based modeling, which can be useful. Cool. Any questions about these ones? Okay. Next, actually, this part might be a little bit simpler than the like knowledge graph-based approaches. So another method for relations extraction is learning from text directly. And the first question about this is, how do you get training data to learn about relation extraction? And so there was this very influential paper, Distant Supervision for Relation Extraction. I would say it's almost one of the first, or certainly one of the most influential papers on like data augmentation or synthetic data for natural language processing. And basically the idea is you already have a knowledge base that has some entries in it, like Wikidata. And so then given an entity relation entity triples, can you extract all text that matches this particular relation type and use it to train a relation extractor, a supervised relation extractor? So the way this works is, like, let's say we have, this is an old paper, so the examples are also old, but let's say we have Steven Spielberg being a director of the film Saving Private Ryan, and that's included in our knowledge base. So what it would do is it would find all sentences that have Steven Spielberg and Saving Private Ryan included in them, and it would label this as like a positive example of that relation. So this is, in general, often it's okay. It works reasonably well. But the problem with this is there are also negative examples of this. So like, for example, here, I think the first one is kind of a negative example for the director relation, because Steven Spielberg's film, Saving Private Ryan, doesn't actually tell you he's the director. It just tells you that he's somehow affiliated with it. He could be the writer, or he could be the actor, or something else like that. So this is a nice way to create data for basically free, but at the same time, you can like create noisy examples, and that can be a problem. So there's been a lot of work about this. Relation classification with neural networks. There's a lot of different methods that could be doing this. Most of them work by extracting features and then classifying somehow, although there are some large language model-based methods now. One thing about relation extraction, or not, kind of like information extraction in general, is that very often you want to run this over like a huge corpus. You want to run it over the whole internet or other things like that. So from that point of view, like I said, I could just ask Mistral to give me the answer about like whether cars are included in sentences. But if you want to run, GPT-4 over the whole internet, That's a pretty big budget, and you might want to reconsider that. So there are also is also some benefit in having cheap and lightweight methods. So basically, what this particular paper did is it extracted features and classified. So it extracted lexical features of the entities themselves and features of the whole span. And so like the way most modern methods for this do this is they basically extract features from the first part of the first entity, the second part of the first entity, the first part of the second entity, and the last part of the second entity, and take all of those embeddings, feed them into like an NLP or something like that, and then make a prediction about whether that relation exists. So if you have an embedding model, this is relatively easy to do. You feed it through like Roberta, or you feed it through Mistral and get the embeddings for each of the tokens, and then you make a prediction based on those 4 embeddings. The details of that are like not super important unless you're going to go in and implement it yourself. So you can like if you're actually going to be doing relation extraction, obviously the details are important, but I'm assuming that most people won't be doing that as your final project. But one really interesting thing that is relevant, even if you're not doing relation extraction, is how you can model noise, because this, as I said, they're creating lots of like semi-noisy data. And a lot of the work in getting good models for relation extraction has been, how do we deal with this distant supervision noise? And I'm just going to give one example here, but there's like a series of papers after this that also tried to do similar things. So the idea is that there's noise in the distant supervision labels. And so we want to model and mitigate that noise. And the way this paper does this is they have an encoder. And from the encoder, you calculate embeddings and make predictions. And so you have a small set of like very high quality data. And this small set of very high quality data, you can basically trust that all of the data is not noisy. Like maybe it's manually annotated data and you have like 5,000 examples of it or something like that. And then separately from that, you have like 5 million examples of automatically labeled data that might be good or might not be good. And so what they do is essentially at the beginning, they take this encoder, get embeddings, make predictions over the high quality data. And then they have a separate noise modeling layer where what this noise modeling layer does is it has a transition matrix, which says, given that we made a particular prediction over classes, because this is essentially a multi-class classification problem, they transform sorry, I don't remember if they transform the probabilities or the logits. I think it's the probabilities, but they transform the probabilities and get a final distribution after noise. And so that means that you can basically smooth out this distribution and account for the fact that the labels may be noisy or may not be noisy. Then they add additional normalization on this transition matrix using something called trace normalization to move this matrix closer to the identity function, which says that the predictions are probably not wrong all the time. The predictions are probably correct, a lot of the time. They're not correct all the time. So then you have that trace normalization competing with this trying to give you like a more smooth distribution and reduce your reduce your loss. So I think this is actually a pretty interesting idea, and it can be used not just for relation extraction, but also in cases where you might have noisy labels overall. So are there any questions about this or any of the things that are going on here? Even if you're completely uninterested in relation extraction, I'd encourage you to think about like what are some examples of things that you are interested in where you could get potentially noisy labels, and how could you account for the noise there? Like that might be a thing to think about. Okay, so this was a very, very brief overview of how we create knowledge bases from textual data or from knowledge graph data, structured knowledge graph data. So now I would like to talk a little bit about how to use knowledge bases to inform neural models. And there's a bunch of different ways to do this. Um, the first way is to improve embeddings with existing lexicons. And this example is using non-contextual embeddings, like not the ones we get from neural language models, but ones we get from just running a embedding model like Word2Vec or something like this. And what they did in this paper is they essentially retrofitted embeddings to existing lexicons by doing post hoc transformations of the embeddings so that they matched the knowledge graph or lexicon better. And so the way they did this is they started out with pre-trained embeddings, and they had a double objective of making the transform embeddings close to the neighbors and close to the original embedding. And the way they did this is they essentially had this regularization term over here. So this regularization term is basically saying, I don't want you to move your embeddings too far away from how they were initialized. And then at the same time, I would like you to make these embeddings closer to each other if they are synonyms of each other. So they did this using WordNet, and they basically took the words that were synonyms to each other in synsets with each other. And they tried to regularize the synonyms to be closer together, but also the embeddings to be closer to how they started out. And there were also examples of forcing antonyms away from each other. So like if you're, this is a little bit of an older work, so it was working on non-contextualized embeddings, but we could do something very similar for more modern models in like knowledge graph embeddings, for example. So let's say we had a model that identifies entities and then different examples of those entities across different contexts. Let's go back to the Wikidata. And so if we had lots of examples of Joe Biden, Joe Biden is referred to in a number of ways, like Joe Biden, Joseph Biden, Joseph R. Biden, JRB, I guess. POTUS 48, 46, sorry. And so you could find different examples of things that match these strings and even do entity linking, which I'll talk about in a little bit. And then encourage the embeddings for all of these different instances to be closer together to make your model like distinguish them less and ensure that they get closer embeddings, and that could improve like question answering, lookup, other stuff like that. Cool. Yeah.
I have a question about this. So what happens if you do like subword modeling and then you don't have like the embedding for that entire string that is supposed to be closer to another string?
Yeah, what happens if you do subword modeling and you don't have the embedding, you don't have a single embedding that corresponds to an entity? So that's a really good question. Let me check. I don't think I actually have these on the slide, so I might have to open a paper. Yeah, okay. So there's a lot of different ways to handle this. So there's two papers. The first paper is a really nice paper, very influential on the subject of coreference resolution. And coreference resolution is essentially trying to identify when two spans correspond to each other. So like if I say Joe Biden early in a document and then later in a document, it just says Biden, we want to know that those two things are referring to each other. And then we had a paper later where we generalized this and applied, very similar methodology to like lots and lots of different analysis tasks. But I can show the beginning here. And basically the methodology that they use here is they had and this is specifically for modeling spans and getting embeddings out of spans of tokens. And what they did is they essentially have a model where you take the thing from the beginning, the embedding from the beginning of the span, the embedding from the end of the span, and the average embedding of all of the embeddings in the span. And that gives you 3 vectors for any span, right? Because you can always get the beginning, the end, and the mean. And then based on that, they feed that through like a neural network and get a new embedding. So they feed that through a transformation and get a new embedding. And so that's the method that they used. And I think our paper actually has a better figure of how you can actually use that. Oh, actually, maybe it doesn't. Okay, but anyway, yeah, because yeah, here's the figure. So then you can use that for a number of things. You could use that to like look up something in a knowledge base. You could also use that to decide whether 2 spans are co-referent by feeding in like the first span and the second span in, and then predicting whether those 2 spans correspond to each other or not. So this general idea of modeling spans and then modeling relations between the spans allows you to solve like lots of different tasks, like part of speech tagging or named entity recognition or relation extraction or other stuff like that. So yeah, actually, I realize now that I should have probably talked about these in the slides where I was talking about modeling, but that would be my recommended way of doing it. Cool. Any other questions? Nice. Okay. So another question is, how can we inject knowledge into language models? There's a bunch of different ways to do this. One very easy way is to somehow look up relevant knowledge in your knowledge graph. And oh, sorry. I was presenting on my own screen, not the screen that everybody can see. So to look up all of the knowledge in a knowledge graph and somehow provide it to the model. One way you can provide it to the model is through prompting. But the problem with prompting is that you're not necessarily going to be able to utilize knowledge that is kind of like minority knowledge, because the embeddings of the entities that you're presenting may not be, like well learned. So you're requiring essentially the model to be able to generalize from the knowledge you provide in the prompt, despite the fact that the prompt is like minor entities or other things like that that are not as well learned. So is another method to handle this. We previously proposed a method that allows you to essentially predict, instead of predicting directly the words here, you can predict a tag that says birth name or a given name or family name or something like that. And then post hoc, the model will fill in that like birth name text based on a knowledge base. So, if you have a Wikipedia article about Barack Obama that you're trying to write, it could predict birth name, comma, born in, birth date. And that's like a very, very common thing in Wikipedia, right? So because of that, it can predict it very consistently, very formulaically, and that allows you to, with high confidence, get something that makes sense and is factual and reduce hallucination and other stuff like that. So basically, how could you inject this into language models? There's multiple ways. One is prompting. That's maybe the easier way. Another way is through like templatic generation like this, where you generate placeholders for all of the information you want to add, and then you add the information directly from the knowledge base through the placeholders later. Cool. There's details about this in the paper, like how we formulate a training objective for something like this. And the difficulty in formulating a training objective is that you need to figure out when you want to replace things. So like you might not always want to replace with birth name, you might want to replace with given name and family name. And we demonstrate that you can figure out how to do this by essentially like marginalizing over the various ways of doing this. But that's kind of more complex detail that's in the paper. Another really interesting question that this is also a paper that I was involved in from 4 years ago, but I feel like this is not entirely solved even in like modern RAG systems today, is how can we reason over a lot of text that's included in a knowledge base? Sorry, reason over text corpus like we reason over knowledge bases. And basically, what we did was we answered questions using text corpora as traceable knowledge bases. And we did relevance matching over mentions. And the way we did this is we created mention vectors. And the mention vectors are vectors of all of the mentions in the knowledge base of particular entities. And then we retrieved relevant mentions from pre-trained models. So we ran embeddings and generated embeddings for each of the mentions in the whole corpus. And based on this, let me find the place over here. So based on this, we basically encoded all of these in here. And then we had a dense query vector. And the dense query vector was specifically trained so that it would be able to identify entity mentions that answered the problem. So if we had like, when was the Grateful Dead and Bob Dylan album released? We would have Bob Dylan be one vector, the Grateful Dead be another vector. And the model would be specifically trained so that when you took the entity embedding of this and matched it with an entity embedding in this big corpus of encoded things here, it would be most likely to return relevant information to answer these like entity relation questions. So then the question is, how do we train a model like this? How do we train like a dense embedding model so that it gets relevant information for answering questions? And basically the way we did this was through weak supervision. Just like I talked about for relation extraction, in relation extraction, we can create weak supervision by taking a big existing knowledge base and identifying all of the sentences where the answer is included. And so what we did is we took this big existing knowledge base and said, okay, what are some of the relations in the knowledge base? One example of a relation in the knowledge base is Steven Spielberg is the director of Saving Private Ryan. So we created questions that said, who was the director of Saving Private Ryan? We can create those with templates easily for many different relations. And then we took the embedding for Saving Private Ryan in that question, and we tried to upweight all of the Saving Private Ryan embeddings over all of Wikipedia, where Steven Spielberg co-occurred in that sentence. So that tries to match artificially created questions with sentences that would be the answer to that question. And so that gives you like supervision, it gives you a lot of data to train over, it gives you a good model. So that allowed us to learn this model well. So this is one example of how you can do like RAG specifically like informed by knowledge bases and stuff like that. Any questions about this or? Okay. So another thing that I'd like to go into is something we call schema-free extraction. And so if I go back to the Wikidata page, Wikidata has something we call a schema. And the schema is basically like, what are the relations that are included in the database? So one of the relations that's included in the database is instance of, I guess, also image. Lots of images. Signature, sex or gender, country of citizenship. And these relations are like decided a priori by the people who created Wikidata. And there's lots and lots of them, but that doesn't necessarily mean that like similarly to the problem of not having all of the entities, we can't have all of the relations. And just to give one example, I was in preparation for our large language models lecture, I actually created some structured data about large language models. And some of the structured data about large language models that I created was like, what is the variety of positional embedding that they're using? Or positional embedding variety. And positional embedding variety is not in Wikidata, I think. I'd be surprised if it was in Wikidata, but I think it's not in Wikidata. So like as you go down to like more esoteric concepts or like specialized domains or stuff like that, you're almost always guaranteed to not, have all of the entities you need or not have all of the relations you need. So that's the problem that schema-free extraction is trying to solve. It's trying to figure out how we can like jointly figure out the schema together with the information we want to extract. And the most famous example of this is something called open information extraction. In open information extraction, basically what it's saying is we don't need a schema. There's no schema. The only schema that we have is the actual text in the sentences that we're referring to the entities. So if we have United has a hub in Chicago, which is the headquarters of United Continental Holdings. The relation is literally has a hub in. That's the relation. And then for this, we have Chicago is the headquarters of. But the problem with this is that this cannot abstract away. So if we had another sentence that said Chicago or United Continental Holdings has its headquarters in Chicago, that would be treated as completely different. You wouldn't be able to like group those two together. So in open information extraction, actually a lot of the methods, this is one of the few things where people still use rule-based systems as kind of like, almost state-of-the-art systems. But basically, the reason why you're able to do this is it's not actually that hard to extract kind of the relevant strings between two entities. And so both the precision and recall are pretty high. And another reason why people use rule-based systems is because they, like you want to run it over the whole web, and running a neural model over the whole web is expensive. So you can use a rule-based model. So some examples of this include text runner and reverb. The basic ideas behind them is that you use a parser to extract, to do a syntactic analysis of the sentence and extract according to rules. So for example, the relation must contain a predicate. The subject and object must be noun phrases, other things like this. And then what they did later is what they did in this paper, arguably this is maybe no longer necessary with the compute power we have now, but they trained an even faster model to extract over large amounts of data. So they basically used this as weak supervision and then trained a model that could do it even faster with a sequence-based model. Another thing that they did was they aggregated multiple pieces of evidence heuristically to find common and therefore potentially reliable extractions. So like any piece of text on the internet like could be a lie, right? So if I might write on my blog, United has a hub in like Denver, or on the other hand, wait, is that right? Something has a hub in Denver, but United has a hub in Pittsburgh is definitely wrong. So let's go with that. So somebody could write that on the internet, and in fact, because I just said it, it's probably in YouTube comments somewhere. But like any piece of information on the internet could be wrong. So basically, they had heuristic methods to filter these out, and usually these were frequency based. So it's like if both United and Pittsburgh are very common, but it's very rare for somebody to say United has a hub in Pittsburgh, then that means it's statistically unlikely for this to be correct. Because if it were correct, we'd expect to see it much more frequently. So those were the kind of things that they did here. There's also some neural models for OpenIE. I think these are used maybe a little bit less often. But basically heuristics are still not perfect. And so what they did, the problem with like not relying on heuristics is you need to get training data from somewhere. So there's a rather clever paper. And again, if you're not interested in relation extraction in particular, I think this is one thing that's still worth paying attention to, which is they demonstrated that it's possible to create relatively large data sets by asking people simple questions. And in particular, they wanted to get relation extraction data sets that are like, who finished something? Like UCD finished the 2006 championships. And if you ask people like, okay, select this span, select the entity span, the relation span, and the in the second entity, the head entity, the relation, and the tail entity. Select it on this interface, and then tell me, is it this relation or this relation or this relation? That's actually pretty hard, and getting like crowd workers to start learning how to do that task is a bit tricky, and it takes some, it takes some time to get them onboarded, basically. But basically what they said is instead we'll just ask them questions where the answer to the question basically gives us the answer to what the relation is. So they ask like who finished something, and the answer is like UCD. And what did someone finish the 2006 championship? What did someone finish something as? And basically, in doing this, they created something called semantic roles, which we're actually probably going to talk about a little bit later, but you can take the semantic roles and then you can use them to annotate relation extraction data. And then they trained a supervised neural tagger for this. Cool. So another thing I'd like to talk about is I talked about learning information about entities from entity embeddings, but you can actually learn information about relations from relation information about other relations. And this can help solve the problem of like essentially the fact that OpenIE is not able to abstract and generalize. So word embeddings or entity embeddings give information of the word in context, which can be indicative for knowledge bases. But other relations or combinations thereof are also indicative of them. And if anybody is familiar with graphs or graph processing, there's the whole idea of link prediction, where you're given like a small number of links in a graph and you want to predict what other links are likely to exist. And like, as I said, a lot of, very prominent AI researchers got their start in relation extraction, and Ilya Sutskever is another one of them, actually. And basically, this 2009 paper proposed to use tensor decomposition to do induction of relations. And the way it worked is you model relations by decomposing a tensor containing entity, relation, entity tuples. So you have the left entity, the right entity, and whether the relation exists is this big tensor in the middle, where these are embeddings of the left entity, these are embeddings of the right entity, and then the depth of the tensor is like which relations exist. And so we know that some exist, so we give them a 1. We know others exist, don't exist, so we give them a 0. And then we do a low rank approximation of this tensor. And if we do a low rank approximation of the tensor, we have reconstruction error, basically. So when we reconstruct the tensor, some things that were previously 0 become 1. And so the things that were previously 0 and then become close to 1 are the ones that we think like actually might exist. They might be real. They might be real relations that we were just missing because our previous knowledge base was incomplete. And one thing that takes us a step further is what if we actually do have a knowledge base, or what if we even have multiple knowledge bases? Like, what if we have Wikidata and we have WordNet and we have other things like this? And in addition to that, we also have OpenIE extractions. So there's an idea of something called universal schema. And what universal schema do is they embed relations from multiple schema or schemata in the same space. And based on this, they then predict which ones are likely to exist or which ones are not likely to exist. So here we might have Freebase or Wikidata. We might have another kind of relation extraction data set called TAC. And then on the training data set, we have like all of these things that are like positive or negative or something like this. And then on the held out data set, we have only information about like OpenIE, for example. So for all of the entities that exist in the knowledge base, we know, whether the relations exist, but for all of the entities that don't exist in the database, we don't know. And so then just from the existence of OpenIE relations or non-existence of OpenIE relations, we can predict that other relations might exist, for example. So this is a great way to combine the two together. Like OpenIE, you can run it over, very large data sets, but it doesn't have a good schema. Wikidata has a good schema, but you can't, it's all manually created, so you can suggest other ones. And one other like interesting thing is you can suggest other things that might exist in Wikidata, but you could also track that back to the original text that indicated that it might exist in Wikidata. So then you could have a human go back and check it to make sure that that's actually true and trustworthy and other things like that. Cool. So if you like tensors or you like linear algebra or things like this is maybe something that you could take a look at and think a little bit more about. Any questions here? Okay, cool. So another thing I'd like to talk about is modeling relation paths. So this is a really nice idea, which is you can make inferences across multiple hops of relations based on particular relations existing. And so multi-step paths can be informative for indicating whether individual relations exist. So for example, given a particular word in a paper title, recommend a venue in which to publish the paper. And so this is the problem that they were trying to solve. And then basically you have a word. You find, if you have that word in your paper title, you then find other papers that have that title, that have that word in their title, and those papers are in a journal. And that gets a high weight with respect to like that, your paper being, relevant to that particular journal. You can also say, okay, I have a word, find papers with that word in the title, find the first author of that paper, find another paper that had that author as a first author, and then find the journal of it. And they demonstrate a way where you can like expand these paths and feed them into a prediction model and use that to predict, additional relations. So unlike this method here, this method was saying like other single relations are indicative of a particular relation existing. This paper is saying not just individual relations are indicative of another relation existing, but actually relation paths are indicative of a relation existing. So this is more expressive, basically. And this follow-up paper, using differentiable logic rules, actually made all of this end-to-end trainable. So this allows you to consider whole paths in a differentiable framework. And so the way they did this is like if you have, city and country and has office in country, city and country and has office in city, that indicates has office in country. And I'm sure, many people here have learned about logic and, induction from or deduction from logic rules and stuff like this. But the problem is deduction from logic rules is very fragile. Like there are cases where there are counterexamples. So if you say that something is always true deductively, then that can cause problems. So in reality, it's like if you have two pieces of information, something can become much, much more likely. And so, just to give an example, somebody studying at CMU makes it very likely, much more likely that they're studying computer science, and much less likely that they're studying medicine or something like that. But that doesn't mean that it like entirely. The first one is definitely not entirely implied, and I'm sure there's like a few people at CMU who are somehow studying medicine through a joint program with Pitt or something like that. So, like it's very rare that logic rules are hard and fast. And so basically what they do is they treat each path as a sequence of matrix multiplies where they have a rule weight like this. And in the end, that allows you to make a prediction about whether a particular logic rule is correct or not. So this is, I've been working mostly in like structured knowledge space, structured knowledge graphs, other things like this. I don't think there's a whole lot of work that directly applies this to language models, like differentiable logic rules in language models or things like that. Just because it's less clean, it's harder. There's a little bit of work which I'm going to talk about now, but I think like this kind of work is interesting because a lot of models are not super great at reasoning, and how to like allow them to be better at reasoning is kind of an open problem. So learning from these older works that did it in a more structured space and trying to figure out how to apply them to less structured spaces is still interesting, I think. So, cool. Then the final topic I want to talk about is probing knowledge in LMs. And so we have these knowledge bases that encode, tons and tons of knowledge, which allows us to figure out, oh, well, how well do language models know about these things? And so traditional kind of QA machine reading comprehension RAG models usually refer to external resources to answer questions like Wikipedia articles or things like this. But then the question is, without doing RAG, can we answer questions like what knowledge is encoded? And so the first paper that kind of handled this sort of problem is this paper, which actually was also called WAMA, surprisingly. They released a resource called Llama, except it was LAMA. But what they did is they in contrast to using structural queries like SQL or Sparkle to query KBs, they tried to use natural language prompts to query LMs. So this was actually one of the first kind of papers on prompting for language models in a way. And the way they did this is they did like Dante was born in mask, and then they tried to fill in the mask using a masked language model and output Florence. So when they did this work, now we don't do this quite as much, but when they did this work, they basically used the knowledge base as the ground truth and tried to probe whether the knowledge included in it in the knowledge base was also recoverable from the neural network. And they proposed the Llama benchmark. Basically, it was manual prompts for 41 relations. They created the prompts manually. So like X was founded in Y, the prompt template. And they filled in the subjects and had the LMs for such as BERT predict the objects. Like Bloomberg LP was founded in Mask. And they demonstrated that like basically Elmo, Transformer XL, and BERT base got up to 31% accuracy. Now I'm sure the modern language models would have much higher accuracy than that. This is a follow-up paper that we did to this, where we tried to do this multilingually. I think this is really, I think one thing that's interesting about this paper is even if you're not interested in multilingual stuff per se, there is an interesting dichotomy about like what knowledge is included in LMs and whether we can retrieve it. And the reason why I'm saying this is because in this paper, we created queries from a knowledge base. And because we created queries from a knowledge base and knowledge bases are multilingual, we can also create multilingual queries from knowledge bases, right? So we can use exactly the same entities, but just ask the same question in different languages. And so we had a bunch of people manually create prompts for all of these languages here. And you can see that in English, it's much better at responding to these queries than it is in any other language. And in particular, like lower resource languages or languages that are less similar to English, it did much worse. And notably, we counted the answer correct if it got it. We had two settings. One setting is we counted the answer correct if it only if it answered in the language we queried it in. But in the other setting, we also counted the answer correct if it answered in any language. So it didn't necessarily have to even know the name of the entity in that language, and we would still count it correct. And so what I mean by there's a dichotomy between the information that language models have encoded and whether they're able to retrieve it is in English, it's able to answer, the models we tested were able to answer like 17% of queries. But if the fact that they're able to answer in English means that the language model, quote unquote, knows the answer, right? Like it knows the answer in English, we're asking exactly the same question in all the other languages. So, it should know the answer in the other languages too, but it's not able to retrieve the answer because we asked in another language. So that brings up some interesting questions about how we can make models better at retrieving the knowledge that they already know in English when you query them in other languages. And there was another paper recently, I don't know if I'd be able to find it exactly, which is they prompted models with personas. And so they said, I am a old man, I am an old woman, I am a young man, I am a young woman, I am a child, or something like that. Or they also talked about things like physical disabilities and things. And they said, please answer this question after they prompted with a persona. And just having that persona greatly changed the ability of the model to answer questions. So it's this very weird thing, which is like the models are actually capable of answering the questions, but based on how you probe them, whether it's in like different languages or if you give them a different persona, they manage to answer things differently. And so on the plus side, like you can make ways to reduce the language model's performance by giving it like a persona that shouldn't be good at answering questions or something like that. But on the plus side, like when you're doing code generation, there was this magic prompt, which is like, I have checked this carefully and all the unit tests pass. And that would improve your code generation accuracy by like five points or something like that. So you just get the model in the right mood to answer the question accurately, and it does a better job at doing it. So it's kind of, it goes in both directions, I guess. Cool. Yeah, any questions here? Another thing that you can do is fine-tune models specifically so they're good at answering knowledge-based questions. So this paper demonstrated that you could fine-tune models on synthetically created knowledge-based questions, and that would improve the ability of the model to answer questions about knowledge bases. It's yeah, it's pretty straightforward. So there's that. Yeah, we already talked about this in the RAG class, so I think I might skip that. A final paper that I'd like to talk about, this is also a paper done by my student Zhengbao Zhang. And this is interesting from the point of view of multi-hop reasoning. And so I talked a little bit about like multi-hop reasoning along reasoning chains in knowledge bases. And this is one example of multi-hop reasoning along reasoning chains within the parameters of the model. So testing whether models can answer multi-hop questions. And basically what we did here is we took a knowledge base, and a knowledge base can have like country is US, president, and then birth date. And so we can create these multi-hop questions, right? And just follow the relation links, and then we know the answer to the multi-hop question by following the link, and we can generate, the question given a template. So we did this and had like question 1, which is return the artist who recorded Party Ain't Over. And then where in Georgia does Usher live? And then we can turn this into a question, in which part of Georgia does the artist that recorded the Party Ain't Over live? And so we now have a multi-hop question. And what we did is we measured whether the model was able to answer the first question, the second question, and the compound question. And what we found is like what we would expect if models were like perfect knowledge processors, right? Is we have like yes on the first question, no, yes, yes on the first question, and no on the first question. And we would expect that basically, if it knew both of the answers to the first question and the second question, it would get the compound question right. And if it got like either of them wrong, it would get it wrong, right? In the ideal world where the knowledge of the two sub-questions is necessary to answer the composite question, and the model is a perfect knowledge processor. And basically what we found, we tried a whole bunch of different types of questions. And what we found is this is totally not the case. Like it's not the case at all. And what we found instead is if it's able to answer the second question correctly, it was much more likely to be able to answer the composite question. Even if it can answer the first question, that has almost no relation with whether it could answer the composite question at all. So it's more like somehow from the answer to the second question, it was able to get the answer right. And it kind of makes sense actually, because like, let's say the answer to the second question is some like really long list, like who are all the presidents of the United States, or something like that. That's just hard to answer. So if I said, who are all the presidents of the country where Washington, D.C. is located in? Like the second question is really hard, so that's hard to get. But if I say, what is the capital of the country? What is the capital of the country where the most people live, or something like that? Even if you weren't sure about the country where the most people live, you could pick a random capital and get it right some of the time, or something like that. So that's what we found in this paper. And I think like another nice thing about knowledge bases is they allow you to ask like really interesting questions like this about what language models know or what language models don't know in a structured way. So I think if you're interested in probing language models and what they know and what they can infer, what logic they can do, that's good. Cool. Yeah, that's all I have for today. Are there any questions or discussion or things like that? Or happy to talk up here too.